You might have noticed by now that not every combination of capacitors can be solved using the series and parallel methods we've discussed. For example, what's the equivalent capacitance of this configuration here, where each capacitor just has the same capacitance C? If you're interested, I encourage you to try and solve for the equivalent capacitance yourself. This combination that you see on the screen here, well, it turns out that just using our knowledge of series and parallel capacitors, it's impossible to find the equivalent capacitance of this configuration. There's no way to simplify this. For example, are any of the capacitors in series? No matter which way we traverse our finger from one element to another, we always hit a node before we can get to another element, so none of them are in series with one another. Turns out we actually have a bunch of branches in parallel, but no branches in parallel with just singular capacitors. Take these two branches here. The bottom one is very simple, it has a single capacitor, but the top branch has a node in the middle which splits between two capacitors into a different branch, so we can't combine the two capacitors in the top branch into a single one, and so it's not possible for us to use our parallel equations. Or trying these two branches here. We have this middle branch, which is quite simple, but then on the left side there's this node in the middle here, which splits the two capacitors. So we can't join the two capacitors in series and simplify that left branch into a single capacitor. So we're just stuck. There's no way we can simplify this configuration of capacitors using our series and parallel formulas. And also, this is actually not like a one-off thing. There are an infinite number of capacitor configurations that are unsolvable using the formulas we have so far. And that, by extension, means that there are an infinite number of resistor combinations that are unsolvable using our methods too. We've got one last trick up our sleeve before we start to wind down DC circuits. Well, two tricks, I guess. We call them Kirchhoffs Laws, named after Gustav Kirchhoff. They might not help us too much with capacitors, which would explain why we didn't introduce them before, but with these laws, we can deal with any combination of batteries and resistors in series, parallel, whatever, the whole 9 yards. Also, with these kinds of configurations, being able to deal with them doesn't necessarily mean we're trying to find equivalent resistances or equivalent batteries or anything like that. It actually goes a bit beyond that. Really, we can use these laws to find any circuit property anywhere within one of these configurations, whether it's the current through a specific branch or the voltage across a specific element, anything we want. Well then, what are these magical laws you speak of, kind sir? Our first law is usually called the Junction Law, or the Junction Rule. It states that at any junction, the sum of the currents going in must equal the sum of the currents going out. Hopefully this one kind of makes some sense. We've already had some experience with currents at junctions splitting off. Like in the previous video, we could have saved all the word salad and just said, by Kirchhoff's first law, I must equal I1 plus I2 plus I3, since I is the only current going in, and I1, I2, and I3 are all the only currents coming out of that junction. So there is sort of an intuitive feeling we already have with this law, but how do we prove that it's always true? Imagine we have some junction here, with some currents, say I1 and I2 going in, and I3, I4, and I5 coming out. You can use whatever currents you want, and however many you want, our end result is going to be the same. Over some tiny time interval delta t, the amount of charge that enters this node is delta q1 plus delta q2, or just I1 times delta t plus I2 times delta t. If I3, I4, and I5 are coming out of the node, then we have delta q3, delta q4, and delta q5 as the amount of charge coming out, or each respective current times delta t. Now imagine if the total amount of charge going in was greater than the amount of charge coming out of the node. Then over time we would have a steady buildup of charge at this node or at this point. But that's not possible. At a single point in space, we can't have charge building up. It's just a point. It can't support any charge buildup. Any charge that enters the point has to leave the point. In other words, charge can only pass through the point. It can't start building up at a single point. And by the same logic, if the total amount of charge coming out were more than the amount going in, we would have charge building up more and more negative at this point. But this junction here, it's just a point in space. So whatever total charge enters the point during some time interval, it has to be equal to the total amount of charge that exits the point. It's just not possible for charge to be generated or destroyed at this point, seemingly from nowhere. Really, Kirchhoff's first law is just a statement of the conservation of charge. Then dividing by delta t on both sides gives us the fact that the total current going into this junction, I1 plus I2 in this case, has to be the same as the total current coming out of the junction, I3 plus I4 plus I5. Honestly, not really much of a proof. It kind of feels like we went in a circle and only looked at a specific example, but really, as long as you start from the principle that charge can't be created or destroyed at a single point, a logical conclusion is just that the currents in total to the currents out. At this point, maybe it's not totally obvious why this is even useful. It seems like an obvious fact in hindsight. So I was hoping we could try making use of Kirchhoff's rules by going through an example circuit. Now immediately we see a problem with this circuit, which is that we can't decompose the resistances into an equivalent resistance because we got these batteries in the way. But again, when it comes to circuits that look like this, we've gone beyond just trying to find equivalent resistances because we can find any property we want instead. Suppose we want to know what the current going through this resistor on top is, for example. We have no way of using the series or parallel rules, so those aren't going to help us out here. Instead, let's try applying Kirchhoff's first law. In order to do that, we need to define currents through every single branch, so any which way works as long as each branch has its own defined current. Let's say this current is I1, and the current in this branch is I2, and the current in the bottom branch is I3. Just choosing arbitrary directions. It doesn't matter so long as we just pick something. Our only condition in using the first law is we have to be consistent with the directions we've chosen throughout working the entire problem, even if some of our original current directions end up being wrong assumptions. We'll see what I mean as we keep moving forward. But now, what can we say at this junction using Kirchhoff's first law? The sum of the currents going in is just I1 plus I3, and the sum of the currents coming out of the junction is just I2 by itself. Then the first law applied to this junction, or this node, would be I1 plus I3, the sum of the currents going in, is equal to I2, the sum of the currents coming out of the node. Okay, making progress. So what if we apply the junction rule to the node on the other side? We see that we just have I2 going in, and we have I1 and I3 coming out as we've defined our currents. So applying Kirchhoff's junction rule to this node over here, we have I2 is equal to I1 plus I3. But this equation right here is exactly the same as the equation from the first node. Each junction gave us the same equation. We have totally redundant information in the second equation, so we can just discard it at no loss. In general, when applying Kirchhoff's junction rule to a circuit, if we have n nodes in a circuit, it usually makes sense to use the law on n-1 nodes to avoid getting redundant information. So like here in this circuit, we have n equals 2 nodes, so it makes sense to apply the junction rule on a total of 2 minus 1 nodes, or just one node, to avoid getting redundant information. I'm not sure if this is a hard and fast rule that applies to every single circuit, but I don't think I've ever seen an exception, so it's probably a very good guideline to follow. So that's Kirchhoff's first law applied to this circuit. Clearly, we can't make much progress with just this equation alone. We have three variables, I1, I2, and I3, and just a single equation. We need two more non-redundant equations in order to actually solve for I1, if that's what we want, and our second law is going to give us those two equations. Kirchhoff's second law states that summing the potential differences of all circuit elements around a closed loop should give us 0. To see why this is true, consider a closed loop within a circuit with a few elements 1, 2, and 3. We don't even need to know what these elements are. Each could be a battery, resistor, capacitor, you name it. However, each is definitely going to have some potential difference across it, either positive or negative. So why don't we say the potential difference across the first element is delta V1, and so on. Now the signs actually matter here, so for the sake of establishing some convention, let's say that our potential differences are measured counterclockwise around the loop. For example, imagine the electric potential along this portion of empty wire is V sub A, and the electric potential here is V sub B. Then we say the potential difference across element 1 is V sub B minus V sub A, not the other way around. If VB is greater than VA, then delta V is positive, and if VB is less than VA, then delta V is negative. That's all. Now imagine if we have some small charge Q that starts at some point. If the charge moves through element 1, what is the change in energy that the charge experiences? The change in electric potential energy that the charge experiences is just Q times delta V1, the potential difference it travels through. And we have a similar expression if we move through the other two elements as well. Now if we end up back at where we started, the total change in electric potential energy that this charge experienced is Q times delta V1 plus Q times delta V2 plus Q times delta V3, just the change in energy it experienced across all three components added together. But if we end at the point we started out at, we have to end up with the same electric potential energy we started out with. The change in energy of this charge should be zero, because if it weren't zero, like say it were positive, that means we could just keep moving this charge in a loop round and round and round, and the electric potential energy of the charge would keep increasing each time for free. We would have an infinite energy producing machine, or a perpetual motion machine, which is not possible by conservation of energy. Therefore, the total change in potential energy must be zero, and since we're imagining the value of the charge isn't zero, it must be the case that the total potential difference across this loop must be zero. That's one logical argument, but if that's not enough for you, let's examine another. We don't even need imaginary charges floating around for this next one. The electric potential at this point in the loop, we can call it something, so why don't we just call it V sub I for initial. Then what's the electric potential at this point here? Well, it's just V sub I, the potential we started out with, plus the change in potential across the first element. How about the electric potential at this point here? It's just the previous electric potential, plus the change in potential across element 2. And the electric potential at this point here? I'll write it down here because we're running out of space up there, but again, it's just the previous electric potential plus the change in potential across element 3. And we're right back to where we started, but we can't end up at a different value for the electric potential now because we already know we started out with the electric potential at this point here as V sub I. It can't magically have changed to some different value just by us moving our finger around a loop like a little kid. Therefore, V sub I, our original potential, must be equal to this final expression we have for the electric potential at the same point. Just subtracting V sub I on both sides, we end up again with Kirchhoff's second law. The sum of all potential differences around a closed loop in a circuit is equal to 0. So let's make use of the second law in our example circuit. In this circuit, we have 3 closed loops here. This top inner loop, the bottom inner loop, and an outer loop. So let's try applying the loop rule to the inner loop on top. Why don't we just move counterclockwise for each of these examples? It doesn't matter if we go counterclockwise or clockwise since we expect the sum to be 0 either way. Then in moving counterclockwise, we traverse the top resistor first, and we see that because we have the current I1 defined as traveling toward the left, our finger passes from high potential to low potential, because the electric potential across the resistor decreases in the direction of current, as the resistor uses up some of that potential and releases it as heat. So we have a decrease in potential, or a negative potential difference, as negative I1 times 200 ohms, the resistance. Remember, the magnitude of the potential difference across the resistor is just the current through it times its resistance. Keeping on going with our finger, we see that we now end up moving across a battery, And specifically because we're moving our finger from the positive terminal to the negative terminal, again, we're decreasing in electric potential. So we say the potential difference here in the direction we're moving our finger is actually negative 3 volts. The electric potential is dropping by 3 volts as we move our finger in this direction. And that's it. We're back to where we started. So the sum of all the potential differences in this loop, and specific to the direction we traverse the loop, is equal to 0. That's our equation for the upper inner loop. Why don't we now try the lower inner loop? For this one, we'll again just go counterclockwise for kicks, and we start by traversing our finger through this 3-volt battery. Now, because in this case we're traversing our finger from the negative terminal to the positive terminal, the potential difference is actually positive in the direction of our finger's movement. We're increasing electric potential here, so we say the potential difference across our first element for this loop is positive 3 volts. Our next element is another battery down here, but in this case we're moving from the positive terminal to the negative terminal. The electric potential is decreasing in the direction of our finger, so we have to incorporate a negative potential difference in our loop rule for this element in this direction. This is negative 5 volts. Finally, we have to traverse this resistor, and this is where it gets a bit tricky. Because we've defined our current I3 to point toward the left in this situation, the current is actually moving opposite our finger's movement. Now it's in fact the current's direction which determines the potential difference across the resistor. The electric potential across the resistor always goes from high potential to low potential in the direction of the current. So actually, counterintuitively here, our finger is then traversing a positive potential difference because we defined our current as flowing toward the left, which establishes how the potential across the resistor changes. And then our finger is moving from a point of lower potential to a point of higher potential. So it's technically a positive potential difference in the direction of our finger, even though it's a negative potential difference in the direction of the current. So we have to add positive I3 times 100 ohms. And that completes our loop. We end up back at where we started. So this is our loop equation for the second loop. We now have the two remaining equations that we wanted, but I want to go a bit further just for practice, and let's try and write the equation for the outer loop, again going counterclockwise here. We traverse this top resistor first, and because the resistor is moving to the left, the potential across the resistor goes from positive to negative, so our finger does as well, and we have negative I1 times 200 ohms. Moving on, our next element is the 5-volt battery down here, and because our finger moves from the positive plate to the negative plate, the potential has decreased by an amount of 5 volts. Finally, because I3 is moving toward the left, the potential goes from high to low in the leftward direction, so our finger actually experiences an increase in potential, where the magnitude of the potential difference is just I3 times the resistance. And we end up back at where we started, so we can set that entire sum equal to 0. That's all the loop equations we can write down, so we won't be needing the circuit anymore, and that will give us a bit more room. Now it turns out this equation we just wrote is actually a redundant equation. It doesn't give us any new information. To prove it, just try adding the middle two equations. You will end up with exactly the last equation. Therefore, we can just discard this last equation down here at no loss. So how do we prevent redundant equations when using the loop rule? One rule of thumb I like to use is to just apply the loop rule to all the inner loops you can find for a circuit, nothing more and nothing less. In principle, this prevents you from ending up with any duplicated redundant equations, and this gives you useful information in each equation. So seeing that's what we've done here, we've not only avoided redundant information in using the junction rule on n-1 nodes, we've also avoided redundant information by only using the inner loops. So with our three equations here, we can solve for any of the currents we want. But what we wanted in the beginning was I1, the current through the top resistor, and we got lucky enough that actually there's an equation we have here with just I1 as a variable. So we can solve for I1 in only that equation, and we end up with a negative 3 volts divided by 200 ohms, or just negative 15 milliamps. But it's weird that it came out negative, isn't it? We haven't really seen a negative current up to this point. This happens all the time when you're working with Kirchhoffs laws, and it just means we made a mistake in the direction for I1. Really, the current is pointing the other way and has a magnitude of 15 milliamps. So now, just for kicks, why don't we solve for I3 while we're at it? We've lucked out with this equation here because we have a single variable I3 in a single equation. So adding 5 volts and subtracting 3 volts on both sides gives us I3 times 100 ohms is equal to 2 volts. Then I3 is just 2 volts divided by 100 ohms, or positive 20 milliamps. Because it's positive, our assumption for the direction of I2 was correct. It really is to the right, as in our original circuit. Now here is where we hit a potential problem. We already determined that actually our original direction for I1 was wrong. The current in that branch is actually going the other way, and it has a magnitude of positive 15 milliamps. That being said though, should we use positive or negative 15 milliamps when plugging in for I2? In order to stay consistent all the way through, we have to use negative 15 milliamps when plugging in. Even though we know I1 points in the other direction, the variable I1 itself we found is equal to negative 15 milliamps. So all we're doing is plugging in for that specific variable. And we end up with I2 being equal to positive 5 milliamps. So our assumption for the direction of I2 was correct as well. So taking note that the I1 direction has to switch because we evaluated I1 to be negative, the true currents through the branches are as you see on the screen. To recap, Kirchhoffs laws helped us find the current in every single branch, and using that information, we could find the potential difference across any element in the circuit, so we have complete information about everything in the circuit. Just make sure whenever you're using Kirchhoffs laws, whatever directions you choose for currents, you stick with them all the way through to the end.
You look funny!